Section 2.4, one-sided limits. The objective is going to be to demonstrate an understanding of and calculate one-sided limits. So as we have discussed previously, for a limit to exist at C, it must approach the same value from both sides of C. In the graph pictured below, the limit does not exist at x equals 0, since the y value is approaching a different value from numbers less than 0 than it does from numbers greater than 0. The function does, however, have one-sided limits. A one-sided limit is exactly what it sounds like. Y is approaching the limiting value from only one side. In the picture above, the limit as x approaches 0 from the left, which would be numbers less than 0, is 0. And the limit as x approaches 0 from the right, numbers that are greater than 0, is 1. So these are what we call one-sided limits. And the notation that we use for one-sided limits is as follows. So if we want the limit as x approaches c from the left, which would always be numbers less than c, then we write the limit as x approaches c with a little superscript of a negative, indicating from the left, of f of x. And as we're approaching from the right, we'll just use that superscript of plus to indicate that we're coming from the right. So basically, we can talk about the limit as x approaches c from the right of this function here at that point. And here we can talk about the limit as x approaches c from the left of this function, which would be that point. So all the limit properties that we talked about in section 2.2 hold for one-sided limits. We have this theorem that says, suppose that a function f is defined on an open interval containing c, except perhaps at c itself. Then f of x has a limit as x approaches c, if and only if it has a left-hand and right-hand limits there, and these one-sided limits are all equal. So in other words, the limit as x approaches c of f of x equals L, if and only if the limit as x approaches c from the left of f of x is L, and the limit as x approaches c from the right of f of x is equal to L. So, for example here, finding one-sided limits. So we want the limit as x approaches c from the left, and also the limit as x approaches c from the right of each of these values. So if we start with the limit as x approaches 0 from the left, we can see that if we're trying to approach 0 from the left, we are not within the domain of the function, and therefore this limit does not exist. But if we look at the limit as x approaches 0 from the right of the function, so now when we're coming from numbers bigger than 0, we can see that the function value is approaching 1. If we look at the limit as x approaches 1 from the left, as we're approaching 1 from the left, so the x values are approaching 1 from the left, we're on this piece of the function, and we can see that the y values are approaching 0. And if we look at the limit as x approaches 1 from the right of the function, as x is approaching 1 on this side, we're coming on this piece of the function, and we can see that the y values here are approaching 1. Okay, so the limit as x approaches 2 from the left. Okay, so now we're approaching the value 2, and we're coming from the left. That will be this piece of the function, which approaches also 1. So remember, we're looking at the y values. The y values are going to 1 here. And if we take the limit as x approaches 2 from the right, we can actually see that the y values are still approaching the same value, which is equal to 1. Okay? And if we look at 3, so 3 from the left, again, if we're approaching 3 from the left, we're on this piece of the graph, and the y values are approaching 2. And if we look at 3 from the right, now we're on this piece of the graph, and the y values are also approaching 2. Okay? And then the last one is at 4, so if we look at the limit as x approaches 4 from the left, that would be approaching from this piece. And we can see here that our y values are again approaching 1. And then if we look at the limit as x approaches 4 from the right, we can see that, again, we have no function to follow from the right of 4, and so therefore this limit also does not exist. So if there are any, if we're trying to approach from a side that is not within the domain of the function, then the limit doesn't exist because we can't approach from that side. All right, so we can basically see the idea here. If we're coming from the left or the right, now notice that at x equals 2, f of 2 is up here at 2. However, the limit as x approaches 2 from the left and the right here are both equal to 1. Okay, whereas at this point here at x equals 3, f of 3 is also equal to 2. And so is the limit as we approach from the left and the right, also equal to 2. Okay, so the value of the function, or what it's defined to be at that point, again, has nothing to do with what the limit is. Here we want the limit as x approaches 2 from the left, and we also want the limit as x approaches 2 from the right. And we also want the limits as x approaches negative 2 from the left, and the limit as x approaches negative 2 from the right. Okay, so that's what this is asking us to find here. All right, so if we're approaching 2 from the left, so that means we're coming on from x values less than 2, and we can see that our y values are actually approaching 0. If we approach 2 from the right, we can see again that there's nothing to the right of 2 in the domain of our function, and therefore this one does not exist. If we approach negative 2 from the left, we can see again that there's nothing to the left of negative 2 in the domain of our function, so this one does not exist. And then finally, if we're approaching negative 2 from the right, we're approaching from this direction, and therefore the y values are approaching 0 again. Okay, so those again are just the one-sided limits graphically. So it says to prove this limit, and so basically in order to prove it, remember that all of our properties limits hold that held for limits hold for right and left hand limits too. So we had shown previously that this limit as x approaches 0 of this function does not exist. And the reason it does not exist is because we cannot approach from values less than 0. They are not in the domain of the function. Okay, but we can approach from values greater than 0, and we can see that that limit is, graphically we can see that that limit is equal to 0. But to prove this, what we can do is use some of our properties of limits. So this limit is actually equal to the limit as x approaches 0 from the right of x. And then our one property of limit is that if I take the square root of the function, I can take the square root of the limit. Okay? And then, of course, we know the identity function here. The limit as x approaches 0 of the identity function is going to be 0. Okay, and so therefore we're looking basically at the square root of 0, which is equal to 0. Okay, so basically we can prove using our properties of limits again that this limit is actually 0 without actually having to look at the graph. Because eventually we want to be able to take these limits or without using graphs. Okay. So the next thing we're going to talk about is limits involving a function of the form sine of theta over theta. So we can see here in this graph, so this is the graph of y equals the sine of theta over theta. And of course, when theta is equal to 0, we have sine of 0 over 0, which is basically 0 over 0. And that's indeterminate. So there's actually a hole in the graph here at theta equals 0. But the graph actually does have a limit. And as we can see from the picture, again, as we approach from both sides, the left hand and the right hand, the values, the y values, seem to be approaching 1. Okay? And so that is actually, in fact, the case. So it can be easily proven by methods not yet discussed, which is L'Hopital's rule. A proof using trigonometry and the sandwich or the squeeze theorem is given in the textbook. But basically, we have the following theorem, that the limit as theta approaches 0 of sine of theta over theta is equal to 1. Okay? And so that basically means that if we can take something and write it in terms of sine of theta over theta, then we can actually evaluate that limit. So for example here, it says to show that this limit is actually equal to 0. And I have a hint here in parentheses that we can use this half angle formula from trigonometry to rewrite the cosine as 1 minus 2 sine squared of x over 2. So if we do that, we can say that this is actually equal to the limit as x approaches 0 of 1 minus 2 sine squared x over 2 minus 1, because I'm just replacing the cosine with this. And then, of course, those 1's will cancel, and so I'll get the limit as x approaches 0 of negative 2 sine squared x over 2 over x. Now we can use some properties of limits to say that the negative 2 can come out, and we can rewrite this as the sine of x over 2 divided by x times the sine of x over 2, because sine squared would be sine times sine. Okay? And so the reason for doing that is, of course, to try to get it into this form here. So we're not quite there yet, because the argument of the sine function here is x over 2. And so basically, I'm going to need an x over 2 in the denominator. So I can think of this as I'm going to multiply the numerator and the denominator of this fraction by 1/2. So this becomes negative 2 times the limit as x approaches 0 of 1/2 times the sine of x over 2 divided by x over 2 times the sine of x over 2. And now using our property that the limit of the product is equal to the product of the limits, this is going to be negative 2 times 1/2. That's the 1/2 there. And then sine of x over 2, according to this theorem, should equal 1, where theta is x over 2 in this case. So this should equal 1. Shouldn't put an equal there. So this is going to be times 1. And then times the sine of x over 2, as x approaches 0, that's going to be the sine of 0, which is 0. And therefore, actually, this whole limit turns out to be 0, which is what we were asked to show. Okay? So now we have basically two things that we can use. If I can write something as the limit as theta approaches 0 of sine theta over theta, we know that this is equal to 1. And we also just showed that the limit as theta approaches 0 of cosine theta minus 1 over theta is going to equal 0. Okay? And so we can actually use both of these things to prove limits. All right, so here's another example using that. So again, we want to show that this is equal to 2/5. So we're going to start by looking at the limit as x approaches 0 of the sine of 2x over 5x is going to equal 1/5. The limit as x approaches 0 of the sine of 2x over x. And so now we have the same sort of thing. I need the thing in the denominator here to match what I'm taking the sine of. So that means I can multiply this by 2, but of course we can't just multiply the denominator by 2 without multiplying the numerator by 2. And so this gives us 1/5 times 2 times the limit as x approaches 0 of the sine of 2x over 2x. And now, according to our theorem, once these two things match like this, then we know that that limit is equal to 1. So this is just 1/5 times 2 times 1, which is 2/5, which we were asked to show. Okay. Sometimes we're going to have to do a little bit of trigonometric manipulation here. So if we remember that the tangent of x is equal to the sine of x over the cosine of x, and also that the secant of x is equal to 1 over the cosine of x, then we can rewrite this limit to be the limit as t approaches 0 of the sine t over the cosine t times 1 over cosine 2t, and then whole thing divided by 3t. Okay, so that doesn't look much simpler right now, but let's simplify it a little bit. So if we think about this inverting and multiplying, that 3t just becomes in the denominator. So this is equal to the limit as t approaches 0 of sine t over 3t cosine t cosine 2t. Okay, so I'm just doing the invert and multiply. And now I'm just going to rearrange some terms. Okay, so I'm going to write this as 1/3, because that 3 in the denominator can come out of the limit. The limit as t approaches 0. And then I'm going to rewrite this as sine t over t Okay, so that takes care of the sine t over t. And then we have 1 over cosine t times 1 over cosine 2t. And now we can use the fact that the limit of the product is going to be the product of the limits. So as t goes to 0, sine t over t goes to 1. As t goes to 0, cosine of 0 is 1. And so therefore this is 1. And then the same thing here. Cosine of 2 times 0 is still cosine of 0, so that is also 1. And therefore this limit should equal 1/3. So that's basically it. So we had basically two things in this section, left and right hand limits, and limits involving things of the form sine theta over theta as theta goes to 0.